Let's take a look at a fully implemented interpreter for a very simple programming language, the Scheme Syntax Calculator language. Scheme Syntax Calculator, or scalc for short, is a programming language that's just a subset of Scheme. It doesn't have define, or if, or and, or any of that good stuff, not even lambda. All it has is plus, minus, times, divide, and numbers. So you can add together 1 and 2, and you can multiply together the result of first adding 1 and 2, and then adding 3 and 4. Addition and subtraction work just like they do in Scheme. If I want to negate 3, I write that. If I want to subtract 10 from 3, I write that. And similarly, if I want to get 1 over 5, I write that. But if I want to divide 5 by 2, I write that. So here's a nice way of having a calculator. It works even if you space things out in funny ways. So I could add a lot of space here. I could stop this expression and finish it down here. I could finish this other expression here, indenting however I want, and it's still going to compute the right answer for me. There are two important parts to implementing an interpreter. One is to take in text and represent it in a way that allows you to evaluate it, and the other is the evaluator itself, the part that takes in the representation of the code and tells you its value. So if I look in this directory, there's the part that takes in text and gives me back a representation of the code, making sure that all the parentheses are balanced. And then there's the part that evaluates those expressions. Let's start with the scheme reader. If I pass in this argument REPL, which I'll explain in a little bit, it's going to ask me to type in some scheme expression. Now, if I type in closing parenthesis, it's going to tell me that it doesn't like that because you don't have an opening parenthesis. But if you type in +1, 2, then it will read it in successfully. This is a scheme expression. It's written like this in Scheme, but the Python program that is interpreting this Scheme code represents it as a linked list containing +1 and 2. If I typed in some more elaborate thing, like I wanted to multiply the result of adding 1 and 2 to the number 4, then I would see this component of a longer linked list that also contains a times and a 4. If you'd like to read about how this works, you're certainly welcome. It's an interesting recursive program, but it's not our focus. Our focus is in taking times +1, 2, 4 and turning it into the number 12. That is the job of scalc, which first takes in this expression and then evaluates the components, figures out that this is 3 and this is 4, and multiplies them together. Let's take a look at the code, and then we'll analyze it. You get an expression, which would be like this in Python. We see if it's a number. If so, we return that number. Otherwise, if it's a link, that means it's a combination. And we need to get the arguments to whatever we're calling, either times or plus or minus or divide, and then apply that. And apply is something that in this interpreter is just restricted to plus, minus, times, and divide, and has some code to do each of those. But I just wanted to point out that the whole interpreter that goes from expressions to numbers, from here to here, is really not a very long program, but it is recursive. To evaluate an expression, you have to evaluate its sub-expressions. Once you've evaluated the sub-expressions, it's time to apply plus, minus, times, or divide to the arguments. And then there's one more piece of code at the end called the read eval print loop. That's what this acronym called REPL stands for. And that just describes how to interact with the programming language. You read in some contents. Now you have an expression. You evaluate it, and you print out the result. If an error occurs, you print out the error, and you keep doing this as long as people are willing to type in expressions in the language. So the calculator syntax, meaning what is a legal expression in the language, is that there are primitives and call expressions, and the primitives are numbers. And the call expressions have to start with plus, minus, times, or divide. That's the whole thing. Expressions are represented as scheme lists, which are in turn in Python represented as link instances. They encode the tree structure of the expression. What do I mean by tree structure? Well, an expression can have an expression within it, or more than one expression within it. Those are the branches of the tree. So the expression looks like this. The expression tree would look like that. That's just a conceptual thing that we use to think about evaluation. But the actual representation in the Python program looks like this: times 3 plus 4, 5, times 6, 7. But that actual multiplication and adding is not part of the form or syntax of the language. That's part of the meaning or semantics. So the meaning or semantics is that the value of a calculator expression is defined as a primitive evaluates to itself, and a call expression evaluates to its argument values combined by an operator according to the following rules. If it's plus, you sum. If it's times, you take the product. Subtraction and division are slightly more complicated. I've tried to summarize them here. They work just like scheme. So an expression that looks like this would have an expression tree where when you do the multiplication, now you can do the addition and get the final answer. Let's watch it work. I'm going to make one little change, which is to trace this and trace that so that it'll print out every time calc-eval and calc-apply are called. I start over, and just like our example, we're going to add together 5 times 2, 3, and times 2, 5, 5. I call calc-eval on the whole thing, which has to evaluate the 5. I get 5. It has to evaluate the times 2, 3, which means it evaluates the 2 and the 3. And now it knows that times 2, 3 is 6 because it applies times to 2 and 3. Calc-apply returns to calc-eval here. And so this also returns 6. And now we've figured out the value of the second sub-expression, but we still have to do the third sub-expression. 2 and 5 multiplied together gives you 50. Now it's time to add. We're adding numbers together, not expressions. We're adding the 5 that we got, the 6 we got, and the 50 we got, and we get 61.